able to identify the next Earth.
Astronomers suspect there could be tens of billions of rocky, Earth-like planets in the Milky Way. Places where perhaps life has gotten a foothold. But life as we know it requires water. How can scientists possibly find this miracle substance on planets light years away? Water divides our living world. Those with it prosper. Those without suffer. Remarkably, the water we drink today contains the same atoms as the water dinosaurs drank 100 million years ago. It's the same water that formed clouds over the early Earth 4 billion years ago. And every organism that has ever existed on Earth has used this single ration of water as the biochemical powerhouse that keeps it alive.
On Earth, all life requires liquid water to grow and reproduce. It's the common ecological requirement for life.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, actually interact with each other, form more complex chains.
It does it with charge. There's positive charges and negative charges separated between the hydrogen and the oxygen in H2O. Those charges break apart the hydrocarbons, the carbon-based molecules that persist everywhere in nature.
Now that's very rare. Hardly any other liquids do that. So liquid water is a natural starting place when you look out into the universe and say, what planets could possibly have life?
To understand how much liquid water is out there, astronomers must first calculate how common water is in all its forms. Amazingly, they find it everywhere they look.
Water is incredibly common. In its gaseous form, we see water vapor filling the space between the stars. We see it in clouds of material that are actually forming new stars and planets right now.
Since water is a fundamental building block of stars and planets, exoplanet worlds must surely have it in abundance. But if you're looking for life, you need to find liquid water, and plenty of it. To find it, astronomers take their cue from a fairy tale.
Everybody knows the famous story of Goldilocks and the Three Bears and the cup of porridge, where one was too hot, one was too cold, one was just right. When it comes to cooking up life like a porridge, you need to have an environment that's not too hot, not too cold, just right. And traditionally, we look for that at a certain distance around a star.
At first, astronomers based this magical distance, known as the Goldilocks zone, on the Earth's orbit around the Sun. But as they found more and more exoplanets, they've had to reevaluate the boundaries for liquid water.
There isn't a single distance. It depends on the brightness of your parent star. A dim star, you need to be closer. A hot star, very bright, you need to be farther away.
Scientists have calculated just how many rocky planets may lie within the Goldilocks zone of their stars. It comes out to over 30 billion potentially watery worlds. Even more remarkably, recent discoveries have shown us it's not just planets that can bask in the warmth of the Goldilocks zone. There may be moons painted blue with oceans too.
Most of the planets we're finding are big Jupiter-sized planets. However, a lot of them are orbiting roughly where the Earth is orbiting the Sun. So even if the planet that we're finding can't support life, it could have a moon with an atmosphere that could support life.
And the biggest of these rocky moons may resemble our home.
There could be billions upon billions of exomoons out there, and even perhaps countless paradises teeming with life.
David Kipping searches for exomoons by looking for double dips in the brightness of distant stars.
We look for exomoons in a very similar way to the way that we look for planets, by looking for them transit their host star. Now, if that planet had a moon, then we should expect to have one big dip due to the planet, and then one smaller dip either to the left or to the right due to the moon.
Habitable exomoons may play host to one of the most spectacular sights in the universe. Imagine a warm, rocky world, just like our own, with oceans and mountains. But in the sky, a massive ringed planet with a fiery sister moon shooting hot magma into space. Exoplanets, and now the vast potential of exomoons, hint at a galaxy filled with the possibilities for life. But a rocky surface and liquid oceans may not be enough. Biology needs the breath of life, air. Backlit by the sun, a halo appears around the Earth. A pale blue ring of light, our atmosphere, and we owe it everything. The Earth's atmosphere provides the gases that fuel the biochemistry of advanced life. But it also protects the oceans from the full fury of the sun's rays, preventing the water from boiling away into space. Without an atmosphere, there would be no wind, no rain, no fresh water, and probably no life.
Atmospheres are absolutely essential for life. Take a look at the planet Earth, and you realize that just like the skin of the apple preserves the apple, well, the atmosphere of our planet preserves the oceans and makes possible the presence of life as we know it.
Scientists, in search of living exoplanets, hope to detect the thin, gassy envelope that should surround these alien worlds. To do it, they're turning to the power of rainbows. In the same way that water splits sunlight into a rainbow, astronomers use instruments to split starlight into a band of colors called a spectrum. It's one of the oldest tricks in science, and one of the most revealing.
Several hundred years ago, scientists first began to take something like a prism and put it in front of their telescope. So they started taking the light from stars like the sun and actually spreading it out into a spectrum. And what they saw was kind of surprising. So instead of seeing a continuous rainbow of light, they saw that rainbow, but they saw these dark lines superimposed on top.
Each chemical element in the star's atmosphere absorbs different parts of the spectrum, creating signature dark bands.
For instance, up at the top, there's a pair of lines in the yellow part of the spectrum which are due to sodium.
Like a DNA profile for stars, spectral analysis has taught us almost everything we know about stars today. But these same lines may hide a marvelous secret: the faint signal of alien atmospheres, and perhaps also alien life.
So the challenge is that these planets are very small and very faint. So we can't actually go and directly measure the light emitted from the planet the same way that we go and measure this lovely spectrum for the sun. Instead, we have to rely on more indirect methods. So one indirect way of doing that is to wait until the planet passes in front of the star.
When the light of a star passes through an exoatmosphere, the gases that surround the planet should stamp their own faint lines on the star's spectrum.
So as we watch the light from the star transmitted through that atmosphere, its atmosphere is going to act like a little filter. So part of the starlight's going to pass through that atmosphere, and we're going to see that imprinting extra lines on it, which are due to the planet's atmosphere. So that change in the spectrum tells us something about the properties of the planet's atmosphere.
The one chemical astronomers most want to find is oxygen, because only life can produce enough oxygen to be easily detected. It's a so-called biosignature. The race is now on to find biosignatures in the atmospheres of rocky exoplanets. And while some groups look for rainbows indirectly, others are tackling the challenge head-on.
27 to 29. All right, we're off.
Ben Oppenheimer is part of a team trying to take direct photographs of exoplanets using massive ground-based telescopes.
Awaiting instructions.
We're within minutes of taking our first long exposure, and I hope it's good.
The greatest challenge to imaging exoplanets is the blinding light of the parent star, which shines tens of millions of times brighter than the planet itself. The trick is to stop the light of the star from entering the telescope's sensors by blocking it, using a series of masks and lenses called a coronagraph.
Right now we're standing right underneath the telescope's primary mirror, and the light comes through a hole in the middle of the mirror and goes into this crazy box here, which is full of optics, motors, sensors, and electronics that all allow us to precisely control the starlight that's coming through the system.
Using state-of-the-art software, they manipulate the coronagraph to black out the unwanted light.
Under good conditions, we can actually carve dark holes into this image of the star so that we can see really faint things in those regions.
Coronagraphs present an intriguing problem, though. Errors within the optics produce tiny flares of starlight called speckles that look just like exoplanets. But Ben has come up with an ingenious way to tell speckles from planets.
So we've developed a technique where we exploit an aspect of speckles, which is that they change position in the image depending on what color you take your image at.
Image processing.
So Ben takes the same image of the star through different color filters and runs them like a movie. The speckles appear to move across the screen, but the planets stay stock still, allowing Ben to easily pick them out.
And so I'd like to point out that there is a little thing right here that if you watch, for you're careful, you'll notice that it doesn't move and the speckles are washing over it.
This stationary blob is a candidate exoplanet. And below it, and to the left, is a second. They both appear to orbit a star around 200 light years from the Earth. Just a decade ago, capturing an image like this through a telescope was unthinkable. But today, thanks to the ingenuity of astronomers like Ben, we have hundreds. And by analyzing the light from these distant worlds, scientists can work out their chemical composition and potentially the fingerprints of life.
At this point, we're studying much larger planets, gaseous things like Jupiter that most likely don't have any kind of life like we know it. But that's a first step. And we're going to fainter and smaller planets as time goes on as we develop this technology.
In the not-too-distant future, scientists may be able to simply scan a star for Earth-like planets and find the signature of life there.
We can look right at the light from a little planet around its distant star, and that opens up a whole range of possibilities for us to not just detect the planet, but to study the planet.
I mean, this all sounds like science fiction, but there is a reality to this. We have a scientific method to actually determine whether there is life on another planet.
Life is one thing, intelligent life, another altogether. That requires billions of years and a powerful force field like the one we owe our lives to every day. If an alien astronomer were to file a report on our home solar system, they might make a surprising observation. Because of all the 8 planets that orbit the Sun, they could easily conclude that 2, not 1, were suitable for life. It's an easy mistake to make, because the Sun has two planets within its Goldilocks zone, the Earth and Mars. Both planets have surfaces warm enough for liquid water to pool on. But while the Earth is blessed with warm, liquid oceans, Mars is dry and dead. The one crucial difference between these two planets could be the key to finding truly habitable exoplanets: a magnetic shield. Our Sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. You know, if there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
So where does the Earth's magnetosphere come from? And why doesn't Mars have one? Actually, in the past, both Earth and Mars had magnetospheres, but Mars lost its around 4 billion years ago, and with it, the potential for life. Both the Earth and Mars were born into a realm of violence. Asteroids smashed into their surfaces, turning rock and metal into a molten mass. As they started to cool, a solid crust formed on the surface. But the molten metal below churned as the planets turned, inducing a magnetic field which rose high up above the surface of both planets. At the same time, active volcanoes pumped gas into the space around each planet. Protected by the newly formed magnetic field, these gases built up into thick atmospheres, creating the air pressure for liquid water to run on the surface. For over 100 million years, both Mars and Earth were warm, wet paradises, primed for life to take off. Then, quite suddenly, Mars's magnetic protection disappeared. The solar wind blew its atmosphere into space, and its oceans boiled away, leaving the dry, sterile red rock we see today.
Mars' fundamental problem is that it's smaller than Earth. And because it's smaller, the internal core of Mars cooled down and solidified. And once it becomes a solid metal, there's no more magnetic field. The magnetic field shuts off, essentially, and the atmosphere, therefore, is vulnerable to both energy and radiation from the sun and the rest of the galaxy, and probably just blew off. Whatever life was on there, at least on the surface, is now completely exposed.
All rocky planets will one day lose their magnetospheres as their cores cool and turn solid. So, to know if an exoplanet is alive, you need to work out if its magnetosphere is still active. But magnetospheres are tough to measure because they are unbelievably weak.
The Earth has a magnetic field of approximately half a Gauss, which, when you think about it, is actually really weak. Our fridge magnets are about 100 Gauss, so they're much stronger.
Exoplanets are too far away for us to measure such weak magnetic fields directly. But there is an indirect method. When electrons in the solar wind interact with a planet's magnetosphere, they emit radio waves that beam out into space, turning the planet into a giant radio beacon. Astronomers like Evgenia hope to use these signals to spot habitable exoplanets. Not only that, the frequency of the signal should also tell her how big the planet is.
If we're looking for the magnetic signature in the radio waves of a giant planet, say a hot Jupiter, we expect it to have a strong magnetic field, and therefore it would have a high frequency. And around 100 megahertz, kind of where the limit of this radio is. However, a weaker field like Earth's requires us to go down to lower and lower frequencies. So instead of 100 megahertz, we go down to 10 megahertz.
But hunting for exoplanets at 10 megahertz presents a unique challenge. Because the Earth's own magnetosphere creates a deafening radio roar at that frequency. So to find alien Earths using radio requires a dish in space.
When we want to look for magnetospheres of extrasolar planets, we really need to get outside of the Earth-Moon system in order to get away from all the radio frequencies that are bouncing around the Earth.
With a slew of new technologies and upcoming technologies, scientists are edging ever closer to the ultimate prize, finding a second Earth.
I wouldn't be surprised if we have that data about an Earth and about life on it around another star in 10 or 15 years. I'm hoping to see that soon.
Using shadows, rainbows, and now radio, we finally have the tools to detect a planet just like our own. But in the rush to find the Earth's identical twin, are we missing something big? What if Earth is an outlier, a freakishly lucky place on the very fringes of habitability? Could there be another kind of planet out there, even better for life? For years, astronomers have scanned the heavens for planets that could sustain life. They've based their search on the Earth, seeking the exact same conditions and the exact same size.
I think right now there's a huge focus to finding Earth-like planets. Now, whether or not there actually is life there, that is another question altogether.
But after 20 years of searching for an Earth clone, the exoplanet hunters may be about to switch targets. Recent observations have revealed a brand new class of planet, and it's one that may eclipse our own home.
We've learned something in the last few years that really shocked us. With the Kepler spaceborne telescope, we have found hordes of planets that are a little bigger than the Earth. We never imagined that there would be such planets. In fact, in our own solar system, there are no planets between the size of the Earth and the next largest planet, that of Uranus and Neptune.
Astronomers call these mysterious planets super-Earths.
Super-Earths are about 3 to 5 times the mass of the Earth, and there's nothing like that here. We don't know what they're like. It's an entirely alien sort of planet.
In just the last few years, astronomers have begun to imagine the conditions on this new class of planet, and they've come to a startling conclusion. Super-Earths could be super-habitable.
There are probably planets out there that are even more hospitable for life. Planets that have even more chemicals necessary to create the organic materials that create life, conditions that make it more likely to get life off the ground.
Imagine a rocky planet, twice the size of the Earth. Dramatic volcanism on the surface betrays a vast heart of fire that beats within its core.
We expect that a heavier Earth will be more geologically active, that the increased amount of geothermal heat within the super-Earth will lead to stronger motions of the magma underneath the crust.
Belching volcanoes dot the surface of this super-Earth. Their gases feed a super-thick atmosphere and help to regulate a super-stable climate.
Many times, life on Earth was nearly extinguished. For example, once upon a time, the Earth was snowball Earth, completely covered in ice. Maybe in these other planets, there are Earths in which snowball Earth never happened, that the climate was always stable and temperate.
The grip of gravity is 3 times stronger here than we're used to. It pulls mountain ranges down to 1/3 the height they'd be on Earth. Gravity also flattens the ocean bed, making shallower seas filled with volcanic island chains. And the nutrient-rich waters that surround these archipelagos provide the perfect conditions for life.
In these other planets, perhaps they have conditions which would make DNA get off the ground much earlier and flourish much more quickly.
Finally, our super-Earth may be protected by a supermagnetosphere.
The magnetic field strength is a condition both of the mass of the planet as well as its rotation speed. And so it is quite likely that a planet that is a couple of times bigger than the Earth's would be able to develop a stronger magnetic field, may shield the planet even better than our magnetic field shields us.
Having a stronger magnetosphere would be a distinct advantage for life on a super-Earth surrounding the Milky Way's most plentiful kind of star, the M dwarf, or red dwarf star. Red dwarf habitable zones are much closer in than the Earth is to the Sun because their host star is so dim.
It's as if you took the terrestrial planets in our own solar system and zapped it with a shrink ray gun and shrunk them down to orbital periods that are less than about 30 days, meaning that they're very close to their stars.
Some astronomers believe these planets are at risk from solar activity, such as deadly flares. But a super-Earth with a super-protective magnetosphere may well resist these deadly rays, allowing life to flourish under a psychedelic sky full of swirling auroras.
If one was standing on a super-Earth, we would see the aurorae come down to lower latitudes. You might get different colors. If I had the opportunity to travel to one of these exoplanets, I would snap that up pretty quickly.
Most intriguing of all, if life does exist on a red dwarf super-Earth, it could be home to the longest-lived civilizations in the entire universe.
The advantage of the M dwarfs is that they last for much longer. And if you had a super-Earth then, keeping a strong magnetic field, going for billions and billions of years, especially now around a red dwarf that is going to exist for billions and billions of years. You might be in that perfect system where life can exist and evolve into even more complex beings than us.
We're getting so close. Our local neighborhood of stars teems with red dwarfs, bursting with the potential for advanced life. But there are also cosmic killers out there, lurking in our galaxy, primed to wipe out life on a regular basis. Is anywhere safe? The exoplanet revolution is in full swing. The Kepler Space Telescope has scanned our local neighborhood of stars for planets, and it's found them by the thousands.
For a long time, we didn't know if the other stars in our galaxy had planets. And for thousands of years, there was no way to answer that question. Finally, now with modern technology, we can do that. And to our surprise, we found they are extremely common.
From Kepler's small sample, astronomers believe there could be tens of billions of rocky, Earth-like planets throughout the Milky Way, where life may already be thriving. But how many of these countless worlds has held on to this life long enough for intelligence to evolve? The answer, surprisingly, may depend on a planet's galactic zip code.
The universe is not a happy, safe place. The universe wants to kill us. It's incredibly violent out there. There are solar flares and supernovae and black holes and colliding galaxies and all these really amazingly dangerous and violent events. It's actually kind of amazing that we're here at all.
In order to develop advanced intelligent life, an exoplanet may have to avoid these cosmic killers for over 3 billion years.
If we look at the history of the Earth, the first thing that happens that's important is the origin of life, right away, very quickly. But then, nothing for a long time. You have nothing but microbes stomping on the Earth.
For the first 2.5 billion years, the Earth was ruled by single-celled goo. Multicellular life has only been around for 1 billion years. Fish for 500 million. Mammals for 200 million. And modern humans have only walked the Earth for the last 200,000 years. The lesson is clear. It takes a long time to cook up intelligent life. But most planets in the Milky Way don't have that kind of time. Astronomers believe that a planet's position within a galaxy may determine if it gets hit by global extinction events.
There's an idea of a habitable zone for a galaxy, and it's in analogy to the habitable zone around stars.
Stars too close to the galactic center are in the firing line from their violent neighbors, which frequently blast them with deadly high-energy radiation.
In the middle of a galaxy, we have a lot of bright stars and young stars and maybe even supernovae going off. And so there's a very harsh radiation field. That's not good for life.
Fired up by the supermassive black hole that sits at the center of the Milky Way, this cosmic kill zone stretches out around 8,000 light years from the galactic center and extends out along the densely packed spiral arms. Any planets that exist within this zone are likely to have their surfaces regularly scrubbed clean of life. Fortunately for us, our home star, the Sun, sits in a relatively empty, quiet zone between two of the galaxy's spiral arms.
So there's this idea that there's a band in the middle of the galaxy that's the galactic habitable zone, where you don't have too many stars going off, you don't have too many supernovae, so it's quiet in that way. Those might be great places for complex life.
These green zones are like the suburbs of the Milky Way galaxy. They're sheltered from the worst of the galaxy's radiation. It's here that Earth-like worlds will have the luxury of long, uninterrupted periods for life to take hold and develop into more complex forms, and eventually, perhaps, intelligent life, like us. The galactic habitable zone is no more than a fledgling theory, but if it's true, it reduces the number of places where advanced life could flourish in the Milky Way. The good news is those places should be near us, and aliens more likely to be on our doorstep. And with our technology getting better every day, it surely won't be long before we find them.
I think in 20 years' time, I'm going to be able to look up into the night sky and say there really is another place I could stand like this and feel at home.
Suddenly we humans will realize for the first time that there are other cultures, other civilizations, probably other religions out there among the stars, and we are just one member of a grand galactic tribe.
To have cousins that we one day may communicate with seems to me to be potentially one of the greatest developments that humanity will ever experience. And if that isn't worth doing, I don't know what is.
SSC disconnect enable on.
Copy that, ELCOM. All systems are go for entry, descent, and landing. Stand by. Stand by.
right. Data's good.
At the dawn of the 21st century, space agencies in Europe and America began making plans to land the first humans on Mars. But manned missions to the Red Planet have been proposed before. For some, Mars holds the answers to mankind's future in space. Others say Mars is too far, too dangerous, and too expensive for humans to explore. And in a world torn by troubles, some say there is no need, or will, for mankind to reach into space anymore. More than 30 years after the last Apollo astronaut walked on the moon, the American manned space program seems to have lost its way, unable to reach beyond even low Earth orbit.
We've got a problem. NASA has been literally going around in circles with its space program for the past 30 years.
Astronautical engineer Dr. Robert Zubrin has been arguing for years that sending humans to Mars is the mission the space program needs.
It's time that we set goals for NASA that were worthy of the risks of human spaceflight. Mars is the next logical step in our space program. It's the challenge that's been staring us in the face for the past 30 years. It's the planet that's most likely Earth. It's the planet that has on it the resources needed to support life and therefore someday technological civilization. It's the planet that will provide us with the answer as to whether life is prevalent in the universe or exclusive to the Earth. And it's the planet that will give us the critical test as to whether humanity can break out of the planet of our birth and become a spacefaring species.
In the early 1990s, Zubrin was the head of the Mars Direct program at Martin Marietta Astronautics. His team developed a mission to Mars that could be done at a fraction of NASA's projected costs. Using only existing technology, Zubrin argues that the first steps on Martian soil could be made within 10 years.
There is absolutely nothing in this that is beyond our technology.
We are not ready to send humans to Mars right now. We don't know how to keep them alive. There are people out there who say we can go to Mars tomorrow. One of my requirements, one of NASA's requirements, is that if we send humans to Mars, we bring them back alive.
For the past 15 years, Zubrin and his colleagues have waged a campaign to convince society and the political class that humans on Mars should be the goal for NASA now. This is the story of our cold neighboring planet and the debate over whether man's fate is tied to the red world. It's the story of an engineer's journey and the battle of ideas over which direction in space will truly benefit mankind.
We're at a crossroads today. We either muster the courage to go or we risk the possibility of stagnation and decay.
The victor in this debate could determine the fate of mankind. Will we become a spacefaring species? Will we live on more than one planet? In the winter of 2003, the Chinese put their first taikonaut in space. The Chinese Space Administration plans to begin a manned program of moon exploration by 2017. The European Space Agency has outlined a plan for humans to the moon by 2024 and to Mars by 2033. And the Russians, building on years of experience, are conducting tests for long-duration Mars missions. In America, with the impending retirement of the shuttle fleet and the completion of the International Space Station, the Bush administration announced in 2004 the Constellation program,
On the moon.
a plan that would return Americans to the moon by 2020. But the program was never fully funded and was eventually cancelled. 2010, the Obama administration announced its vision for NASA and human Mars exploration.
By the mid-2030s, I believe we can send humans to orbit Mars and return them safely to Earth. And a landing on Mars will follow. And I expect to be around to see it.
With a new timeline for humans to Mars sometime after 2035, and with administrations changing every 4 or 8 years, it is far from certain that such a plan will be realized. 20 years earlier, the first President Bush also proposed a long-term human exploration program, under great fanfare. The program quietly died in Congress a few years later.
If you want to go to Mars, you cannot do it in 30 years. You can't do it in 20 years. You've got to do it in 10 years or less from program start, or you're more or less guaranteeing political failure.
To date, only the Apollo moon program, which was announced in 1961 and had men on the moon 8 years later, has succeeded in getting astronauts beyond low Earth orbit.
I was 5 when Sputnik flew. And while to the adults, Sputnik was a terrifying event, to me, as a child who was already reading science fiction, it was exhilarating, because it meant that this possibility of a spacefaring future was going to be real. And I was 9 when Kennedy gave his speech committing us to the moon.
Go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I grew up during the 60s, when it was Mercury, it was Gemini, it was Apollo. Every month, NASA was doing something more impressive than in the month before. We were going to be on the moon by 1970, Mars by 1980, Saturn by 1990, Alpha Centauri by the year 2000. We were moving out, and I wanted to be part of that. And so I got myself a scientific education. But then, in the early 70s, it's all collapsed. We achieved the first part of that program, Moon by 1970, but the Nixon administration shut down the rest, and we did not move out into space. And for a while, I accepted that, grudgingly. I became a science teacher. But then in the early 80s, something hit me, and I said, I'm not going to accept myself doing less than what I had dreamed of doing when I was a boy.
Zubrin went back to graduate school, getting advanced degrees in engineering and aerospace. He then went on to work at Martin Marietta, which later became Lockheed Martin, designing interplanetary missions. It was here that Zubrin's obsession with the red planet began to take hold. While at Martin in the 1990s, Zubrin and his colleagues developed a plan for sending humans to Mars that changed NASA's thinking on the issue. But the plan has languished on the drawing boards ever since. Now, as president of the Mars Society, Zubrin is at center stage in the debate over the future of manned spaceflight. Known as a smart, visionary scientist, he has authored several books on exploring space and is the self-appointed spokesman for the possibility of colonizing Mars.
Mars is where the future is. Mars is the closest planet to the Earth that has on it all the resources needed to support life and therefore technological civilization. It has water, it has carbon, it has nitrogens, it has a 24-hour day, it has a complex geological history that has created mineral ore, it has sources of geothermal energy. Mars is a place we can settle.
One reason for such optimism over a frozen world like Mars is evidence that 2 billion years ago, Mars was a much warmer and wetter place.
We think that at one time in the ancient past, Mars was very similar to the condition of early Earth.
This Martian warm age lasted for over 1 billion years and could have been a suitable environment for the development of life.
If we go to Mars and find evidence of a second genesis on Mars, I think we can conclude that the universe is full of life. We can probably conclude that on some planets that life evolves to more complex forms, and I think we'd be reasonable to conclude that intelligence could also emerge on some planets as well. It really does answer the question, are we alone? And that to me is a question that transcends science. It's a philosophical, societal, as well as scientific question. To me, that's the big prize. That's why Mars is interesting. That's why human exploration makes sense.
Space programs are often criticized for the huge sums of money they require. Although the American space program is less than 1% of the federal budget, a human mission to Mars may have to wait for better times.
There are those who say that we have many problems to deal with here on Earth, and we need to postpone ventures such as the human exploration on Mars until these problems are solved. Well, there were many problems in Spain in 1492, and there still are. There are problems that need to be dealt with here on Earth, and should be dealt with. But we also have to think of the future. We also have to think about opening up new volumes in human history. I believe that it's essential for a positive human future that humanity expand into space. The greatest value that we got out of Apollo was the creation of intellectual capital through the inspiring of millions to go into science and engineering to be part of the great adventure of human expansion into space.
There's a phrase that happened with the Apollo program, which was, if we can go to the moon, we can. And then everybody's filled in whatever they were interested in. Build mass transit, cure cancer, do this, do that. The point is, it did give us a sense that we could accomplish great things. It did bring out the best of us.
We excited a generation of engineers and scientists. The generation that built the computers and cell phones and all the technology everybody uses today and takes for granted.
If we set humans to Mars as our goal, we'll get millions of new scientists that will create new inventions, new industries. This is the enormous payback, and we can get it if we set the kind of challenge that will inspire the youth.
To Zubrin, civilizations like people thrive on challenge and decay without it.
We have everything we have today because of our predecessors who had the courage to leave the world of the known and go out into the wilderness and build new cities. And if we stop being people like that, then we will hand down much less to our posterity than our ancestors handed down to us. So there's the choice in life. One either grows or one decays. Grow or die. I think we should grow.
History proves that we have never lost by pressing the limits of our frontier.
In the summer of 1989, the first President Bush announced the Space Exploration Initiative, directing NASA to draw up long-term plans to get humans back to the moon and begin developing a program of manned Mars exploration. At Martin Marietta, Zubrin and his colleagues looked forward to moving NASA's space program outwards after 2 decades in low Earth orbit.
Of course, we were very excited when Bush made his call saying that he was making a national commitment to implement such a program.
NASA assembled a large team to take on the space initiative. In 90 days, the team developed a 30-year plan that required an enormous buildup of space infrastructure.
What the NASA bureaucracy decided to do was basically design the most complex mission they possibly could in order to make sure that everyone's pet technology would remain mission critical, which is the exact opposite of the correct way to do engineering.
First, NASA would triple the size of the planned space station and add enormous hangars, as well as free-floating fuel depots, checkout docks, and cruise stations. Then, on the moon, they would construct more shipbuilding facilities, bases, and depots. Next, the moon crew would construct the Mars ship, a huge craft dubbed by its detractors as Battlestar Galactica. This ship would carry everything to Mars over an 18-month flight. Once in Mars orbit, a small group would descend to the surface, spend a few days, then plant a flag in the ground and go home. plan became known as the 90-day report.
To those of us at Martin who had been engaged in designing Mars missions, when they saw the monstrosity of complexity of the 90-day report, we were dismayed, and it was readily apparent to anyone with any insight that that program would fail politically.
The plan was submitted to Congress. The estimated cost, $450 billion. The legislators went into sticker shock. This would have been the single most expensive program for the United States since World War II. By the end of 1990, Congress had refused all requests for SEI funding. When the realization came that SEI was doomed, Zubrin wrote a memo to his colleagues at Martin Marietta, outlining his problems with the NASA plan and arguing for a more direct approach. Zubrin favored launching a Mars mission directly from the surface of Earth, using only existing rocket technology. This negated the need for a lunar base and avoided the complexity and cost of building ships in space. He also objected to NASA's plan for a short surface stay on Mars, a mission that would amount to little more than a flag and footprints exercise. To Zubrin, we were going to Mars to explore and develop a new world. To maximize surface time, Zubrin proposed using a faster flight path, known as a conjunction-class mission. This would mean a crew could arrive on Mars after only a 6-month journey. They would then remain on the Martian surface for a year and a half. This would give the team time to explore a wide area and conduct detailed research about the planet. Then, as the Earth return window opens, the crew would launch from Mars for the 6-month trip home. Zubrin was convinced that a simplified, more robust and cost-effective mission could be designed using these principles. Along with several like-minded colleagues, Zubrin decided to ask management at Martin to allow them to design alternative Mars missions.
The management approved that, and we formed a team that was known as the Scenario Development Team of just 12 people from the whole very large Martin company.
One team member, whose thinking was closely aligned with Zubrin's, was David Baker.
I went off to my office and said, all right, how would I do a Mars mission if I had to pay for it and I had to go on the ride? And I said, well, it's going to be simple. There's going to be no on-orbit assembly. I really tried to take everything out of the mission that didn't absolutely need to be there.
While the rest of the team focused on longer-term, more traditional mission plans that required on-orbit assembly, Zubrin and Baker decided to collaborate on a mission that could be done near-term.
We decided to do Mars the way Lewis and Clark did America. Okay? Use local resources, travel light, live off the land.
Zubrin and Baker were convinced that a Mars mission could be launched directly from the ground. The other team members felt this was impossible, that the weight of the rocket fuel required for a round trip to Mars was so enormous it would render the launch ship impossibly heavy. To solve this problem, Zubrin was exploring a radical idea that had been kicked around the aerospace industry since the 1970s. The idea was to produce a methane-oxygen rocket fuel directly from the Martian atmosphere. It was a relatively simple and robust chemical engineering procedure that was done commonly in the 1800s, the era of the gaslight. If the idea worked, astronauts could land a relatively light ship with empty tanks. They wouldn't have to ship all the fuel with them for their return trip. This would radically lower their size and weight. The only problem was methane-oxygen fuel requires a hydrogen component. Hydrogen exists on Mars in the form of H2O, but water may be difficult or impossible to extract from the Martian environment.
Really, the hydrogen was only 5% of the total weight of the methane-oxygen propellant being manufactured. So if you just say, okay, we won't be pure, we won't get all of the propellant from Mars, we'll just get 95% of the propellant from Mars. The other 5%, the hydrogen, we'll just bring from Earth.
Another fundamental resource that could be extracted from the Martian environment is oxygen. A second processing unit could separate oxygen molecules from the thin carbon dioxide atmosphere, providing breathable air for a Mars crew.
If used intelligently, the same resources that make Mars interesting are precisely what could make it attainable.
Baker and Zubrin had greatly reduced their mission mass, but they still found their ship was too heavy and would require 2 launches and assembly in space. Then Zubrin hit on an idea.
Well, one of the key events of the Mars Direct development was one morning Bob burst in my office and said, "I've got it."
The idea that I finally hit on in 1989 was that we would split the mission up into 2 parts, and we'd send the return vehicle out first with its own return propellant plant. So the propellant would be made on Mars before the first astronauts ever left Earth.
With 2 separate direct-to-Mars launches, a human crew would have a fully fueled ship waiting for them on the surface of Mars before they ever left Earth. So Zubrin and Baker had come up with a plan that seemed to accomplish all of their goals. It was relatively inexpensive, development time was short, they could use existing technology, and it allowed for a long stay on the Martian surface. They dubbed their idea Mars Direct.
SSC disconnect enable on.
35. Let guys go. Hydraulics go.
Aboard an Ares rocket is the Earth Return Vehicle, or ERV. No one is aboard this ship. It will pave the way for the astronauts who, years later, will use the ERV to return to Earth.
1. And liftoff.
On its second day, the ERV deploys a small nuclear power reactor. The reactor powers a chemical plant inside the ERV. The plant will produce the methane-oxygen rocket fuel for the launch home. Nearby, a second robotic rover is guided to a pre-picked landing site for the human crew. It places a radar transponder to help guide the astronauts in. The long journey to land a human being on Mars begins.
3, 2, 1, engine start.
Carrying the most skillfully assembled flight team in history, 4 astronauts begin their 2.5-year mission to the Red Planet. This will be the first time a human has gone beyond the Earth-Moon system, 250 million miles farther than any person has ever been. To counter the health problems of zero gravity and to fully acclimate the astronauts to Mars, the ship will deploy a weighted tether attached to the last stage of the spent rocket booster. By thrusting the ship into a rotational spin, the counterweight of the rocket will create centrifugal force and thus artificial gravity. The crew will be able to live with their feet planted firmly on the floor during their 6-month transit. But the HAB is not entirely alone on its journey. Just ahead of it is a second ERV, identical to the first. Launched just a few weeks prior to the HAB, it will prepare the way for a second human crew that will follow 2 years later. It can also function as a backup for the first mission if anything should go wrong. the 6th month of the flight, the crew will gaze upon an alien world. This is the new frontier.
Oh, spectacular. Just spectacular.
After days in orbit and satisfied with the landing conditions, the crew will receive final word from Mission Control on Earth.
All systems are go for entry, descent, and landing. 3, 2, 1.
It will be a tense 40 minutes before people back on Earth get the signal from Mars and know if everything has gone well.
Okay, 75 feet. Car's looking good. Down a half. Pitch forward. 60 seconds. Lights on. Forward. Forward. 40 feet down. 2.5. Big shadow. 4 forward. Drift into the right a little. 30 seconds. Forward. Contact light. Okay, engine stop.
We're seeing it on the LTP. We're on Mars, everybody.
For more than 500 days, the astronauts will live on Mars and embark on one of the greatest journeys of discovery in the history of science. Will they find life? Or the fossilized remains of past life? Such a discovery could tell us whether our solar system has seen more than one Genesis, and answer the ultimate question: are we alone? In any case, these explorers will be learning how feasible the colonization of Mars really is, and whether or not mankind has a future among the stars. Then, when the time comes and the window for Earth return opens, the crew will climb into their Earth return vehicle and head home. They will arrive home heroes, the first to stretch the limit of man's expanse from one planet to another, their names added to the list of great explorers of new worlds. In their footsteps, others will follow. What began as a trickle is free to rise into a deluge of humankind, sweeping over a once barren land and transforming it into a viable new world. When Baker and Zubrin presented Mars Direct to their bosses at Martin, they expected the worst. To their surprise, management was excited about it. They liked the fact that everything needed was relatively simple and near-term.
As time went on, Martin Marietta embraced Mars Direct as their creation and put Bob and I on an airplane to several NASA centers to present Mars Direct and try to build some momentum for it.
Baker and Zubrin flew to the Marshall Space Flight Center in Huntsville, Alabama. This had been one of the original design hubs for the Apollo moon landings, but recently many of the engineers had become demoralized by the failure of NASA's SEI program. Tag team style, Baker and Zubrin presented their alternative mission architecture. The response was thrilling. The old-school Apollo crowd embraced it. This was a plan that actually made sense and was within reach.
Baker and I gave a number of briefings. The first was at the Marshall Space Flight Center. Next was at Johnson. These people were incredibly excited.
Over the next few weeks, Zubrin and Baker were flown around the country, pitching to all branches of NASA. And everywhere they went, the response was electric. The plan was standing up to scrutiny, and groups all over NASA were converting to Mars Direct. Their tour culminated in a public presentation to the National Space Society. The crowd gave the two aerospace engineers a standing ovation. week later, the story was in newspapers around the country. But a counterattack was beginning to form within NASA. The space station teams and many in the advanced propulsion groups were against the idea. Since Mars Direct didn't need their programs, they felt under threat. As quickly as doors opened for Zubrin and Baker, they began to close.
NASA didn't want to pursue a Mars mission at that time. They didn't want to be derailed by a bunch of Mars fanatics that thought that their idea of what NASA should do should overwhelm what NASA thought NASA should do.
What we did in Mars Direct was literally come up with the leanest solution, the one that involved the least spending on an assortment of technologies and infrastructural elements, including, for example, we made no use whatsoever of the International Space Station. And so people involved in all those programs were very upset because we were showing that you could go to Mars without their program being required. And they felt that we were de-justifying them.
The NASA administration rejected Mars Direct. The two engineers were outsiders again. But Zubrin remained determined.
Bob had grabbed hold of it, and I could see that it was his, and no matter what I did, he was going to do what he was going to do, and he was going to be a proponent for it and push it, and I really saw my role sort of evaporate. It's a little bit like being a dim planet next to a bright star around him in terms of his enthusiasm, and you really can't compete with that. All you can do is decide how you're going to deal with it.
By February 1991, Baker quit Martin to start his own firm. Zubrin battled on. For the next year and a half, Zubrin tried to get NASA to pay attention, giving speeches, writing papers, but Mars Direct's time seemed to have passed. But then in 1992, a new administration came into power at NASA, and Zubrin saw a second chance.
I was invited to brief Mike Griffin, who was the Associate Administrator for Space Exploration in charge of the whole Space Exploration Initiative. He immediately became a very strong supporter of Mars Direct.
But before the engineers at NASA would take another look at Mars Direct, they wanted Zubrin to prove that producing rocket fuel on Mars could work. They gave Martin Marietta a small budget to do an experiment. Zubrin and his team built a machine called the In Situ Propellant Plant. It could take carbon dioxide, the dominant gas in the Martian atmosphere, combine it with a little hydrogen, and produce a methane-oxygen fuel.
We did it in 3 months with a very small team. We built a plant that was 94% efficient, and no one who actually participated in that effort was actually a real chemical engineer. They were all aerospace engineers, like me, who were simply dabbling in chemistry in order to prove to NASA that 19th century chemical engineering really worked.
With the experiment a success, the administration had Zubrin give detailed briefings of the mission plan to the engineers at the Johnson Space Center. They liked it, but had some problems. Dave Weaver was the lead mission architect.
There were a number of things that we were concerned about with Bob Zubrin's mission. First of all, we thought his estimates of mass were probably too optimistic. Didn't have sufficient margins for a variety of things, not the least of which would be things like provisions for the crew, the amount of water that would be required. We thought his ascent vehicle was very large, which meant his power requirements, his propellant requirements were much larger than needed to be. His trip times out were too long, and that for very little effort you could get them shorter. The other problem was the size of his crew. He had a 4-person crew. I think virtually every study that's been done says that a 4-person crew for a 3-year type of mission is probably not realistic.
Weaver took Zubrin into his office, and the two men worked out compromise mission architecture. First, Weaver wanted 3 launches for every mission instead of 2. The first year, 3 ships would launch: a MAV, Mars Ascent Vehicle, an unoccupied HAB, and an ERV, Earth Return Vehicle. The HAB and MAV would land on the surface and begin producing fuel for the return flight and air for the crew. These craft would spend 2 solitary years on Mars, allowing NASA to test all of the systems before sending a human crew. Then, in the 3rd year, 3 more ships would launch, this time with the HAB occupied by astronauts. The other 2 ships are for a future mission, unless needed as a backup for this crew. Once on Mars, the team could also utilize the first HAB. Then, after a 1.5-year stay, the crew would climb aboard their small capsule and rendezvous with the return ship. This ship would carry them back home in a roomier environment than Zubrin's ERV. Zubrin called the plan Mars Semi-Direct. NASA called it the Design Reference Mission.
They had a larger crew than we had. They had bigger ships. They had more equipment. They had heavier equipment. So they had to do the mission in 3 launches instead of 2, but it was done with the same principles of Mars Direct.
The plan was subjected to the same cost analysis that tagged the 90-day report with a $450 billion price tag. The Design Reference Mission came back at a fraction of the cost, $55 billion. Spread out over 10 years, it could be done within NASA's existing budget. The plan made the cover of Newsweek. Here was a mission architecture that was affordable and could be done today with existing technology. But NASA's astronauts have not left low Earth orbit since. With the completion of the International Space Station and the retiring of the Space Shuttle program, a debate rages over the future of space exploration. Should NASA continue to focus on low Earth orbit, developing technologies for the future? Or should NASA have a goal, like it did in the 1960s with Apollo?
The way we got to the moon was by a presidential imperative that demanded that NASA get to the moon within a decade. So NASA was forced to sit down, design a plan for how to do that, and then fly the mission. Since that time, without the presence of a driving imperative, we engage in basically a random set of constituency-driven programs which are justified ad hoc afterwards by the argument that they could prove useful at some time in the future when you actually have a plan to go somewhere.
I think NASA has focused on a steady process where the government can't just pull the plug on their funding. I think the Apollo cancellation was very traumatic for NASA, and it really transformed NASA from what it was in the 60s to more of what it is now. If you have a singular program like going to Mars, then it is very vulnerable to having its funding pulled.
NASA must be destination-driven. It is the only thing that allows the agency to be productive. NASA was 100 times more productive when it was destination-driven than in the period that it has not been. And we have stagnated in NASA since 1973. 30 years, more than a generation, has been wasted. The American space program's been stagnant for 30 years. There's a once-in-a-generation shot right now to get it moving again by giving it a goal that'll take it somewhere. So the stakes today are high. And if you ask me if I am nervous right now, I am.
Dr. Zubrin.
Why is NASA stuck in low Earth orbit? The problem with NASA's lack of current achievement is not money. The problem is lack of focus, it's lack of a goal. It shouldn't be humans to Mars in 50 years. It should be humans to Mars in 10. We can do this. We do not need gigantic nuclear electric spaceships to send people to Mars. That is pork, it's nonsense. The primary question I get from the American people is, why aren't we doing this? There's a big sense of disappointment, almost verging on a sense of betrayal. The purpose of spaceships is to actually travel across space and go to new worlds, not to hang out in space and observe the health effects from doing so.
Dr. Zubrin, in your testimony, you were very passionate, but you also were mad. You're mad we haven't done this, or that this vision has been stolen from a generation?
I guess you could say that. It's like Columbus coming back from the New World and Ferdinand and Isabella saying, so what, forget it, burn the ships. Okay, that's what has happened in this country. We've won our point that there needs to be a destination. The point we need to win on now is that the destination needs to be Mars, and it needs to be soon.
The movement to send humans to Mars in the near term began at the University of Colorado in 1978. A graduate student in astrogeophysics named Chris McKay gave a small seminar on the possibility of introducing life to Mars.
I got interested in Mars in graduate school. I entered graduate school the same year that Viking landed on Mars and sent back these images, and it sent back data that showed all the elements needed for life are here on this planet, and yet there's no life here. I thought, oh, that's odd. It's sort of the lights are on and nobody's home. And I thought, well, that's curious. So some of my other grad students and I, we sort of got together to talk about, well, if there's no life on Mars now, could we put life there? And that evolved also into the question, well, maybe there was life in the past, and we could find fossils, evidence of it. Well, how would you do that? Well, you do that by sending people there.
Together with fellow graduate students, the group decided to put together a small conference to discuss the matter of human Mars exploration.
We basically just started a forum. We invited everybody from all the NASA centers and from all the universities that were involved in it, and they all came. And it really was, in retrospect, I realized a very important step toward building a consensus for human exploration of Mars.
In 1996, I published my first book, The Case for Mars, and the response was phenomenal. I got 4,000 letters from all over the world. I had Parisian bankers and 12-year-old kids in Poland and firemen from Saskatoon and astronauts, and they're all writing me and saying, how do we make this happen?
Bob Zubrin came to the third Mars conference and got very much involved. And he was willing and interested in forming a society, forming a group and organizing.
He said, look, if we could pull these people together, if we can get them to work together, we could have a force that could actually make humans to Mars happen.
The group formed the Mars Society. Robert Zubrin became the president. They held their first convention in 1998.
The convention was just magic. We had no idea how many people were coming. They were there not just from the United States and Canada and Europe. They were there from Israel. They were there from Mozambique. They were there from New Zealand. It was astonishing.
Since its inception, the Mars Society has attracted members worldwide. Derek Shannon is the head of the Southern California chapter. He's met with political leaders from all over the country.
If you make them look at the whole Mars vision in historical terms, it becomes a much easier sell. How will the Martians remember our century? They're probably not going to remember our deficit, our wars, our healthcare. Those will be footnotes. What they'll remember is that out of all of human history, there came a generation that decided to take this amazing step out into space. And if you tell politicians that they're the ones whose names actually get to be remembered, that's when, hopefully, the space program starts going somewhere.
In order to further the knowledge necessary for a manned mission to the Red Planet, the Mars Society has been building research stations around the globe, all of them based on the design of Zubrin's HAB module. Most recently, the Society set up a desert research station in Utah. Here, international researchers and aerospace students come to do experiments under the harsh desert conditions and learn what's necessary to keep a Mars crew alive and productive.
Basically, what we're doing here is undergoing analog studies. Crews of up to 6 people at a time come together to live in a full simulation environment for up to 14 days. So what that means is every time we go outside the HAB, people have to don spacesuits. They have to depressurize. When we go outside, they're called extravehicular activities. They can only be of a certain duration due to the air supply. We have to recycle all our water and basically have our own food as well.
It's great to fantasize, but it's another thing when you have to put it together, when the nuts have to fit the bolts.
Like the Apollo missions to the moon, sending human beings to Mars will mean putting people in harm's way. There are many dangers in outer space, and many things could go wrong. A serious equipment breakdown could doom the crew to their deaths. Some argue that the risk of failure is simply too high.
You know, back in the days when medieval man was looking out from Europe and thinking about exploring the world was unknown, and map makers populated their maps with dragons. We've got the same thing today. There are people who are afraid to go out into space, and they've populated their maps of the solar system with dragons. You know, we've got cosmic radiation, we've got zero gravity, we've got back contamination. But these are dragons that we can take on.
There are two kinds of radiation astronauts must contend with in outer space: solar flares and cosmic rays. Solar flares are floods of protons that burst from the sun at irregular intervals and would be dangerous to an unshielded human crew.
We are not ready to send humans to Mars right now. We've got to know a lot more about radiation and radiation mitigation. One of the Apollo flights barely missed, like by a week, a major solar event. If it had gone off when the Apollo astronauts were on the way back and forth to the moon, they would have gotten their entire lifetime radiation dose in that one mission. And that's just one solar flare. So that's why we worry about this.
In the Mars Direct plan, Zubrin envisions a central, insulated core where a crew can retreat to while the radiation passes by. The core would be surrounded by all the provisions of the mission. This should stop any harmful dose of radiation from reaching the astronauts.
Basically, you use your pantry as your storm shelter. So a solar flare happens, the alarm bell rings, the crew goes into the storm shelter, they stay in there cramped up pretty tight for a few hours until the all clear rings and they come out. This is going to happen once, it might happen twice in the course of the mission.
The second type of radiation is cosmic rays. This constant rain of charged particles comes from interstellar space and cannot be avoided without many meters of shielding. We can experience some of this type of radiation on Earth at high altitudes. Airline pilots who spend their careers flying high in the atmosphere can receive almost as much of this radiation throughout their life as a Mars astronaut would on a 2.5-year mission.
It's a long trip. It's a 6-month trip there, a 6-month trip back. It's probably a year on the surface. That's a lot of radiation.
The best estimates are that the magnitude of that dose is not that great, perhaps 60 rem of radiation scattered over 2.5 years. Now, 60 rem of radiation delivered over a long period of time like that would not create any noticeable effects at all. It would, though it is believed, increase your statistical risk of getting cancer at some point later in your life by about 1%. Right now, if you're an average American and you do not smoke, you have a 20% chance you're going to die of cancer. This would make it 21. If you're an average American smoker, it's 40. So in fact, if you recruited the Mars crew out of smokers and sent them to Mars without their tobacco, you would be reducing their chance of getting cancer.
With the immense distance from Earth, never before experienced by a human being, with the constant dangers of outer space surrounding their small, life-sustaining craft, and with nowhere else to go, the psychological impact on a crew could be severe.
Fear is real. I mean, it would be, to me, abnormal for a person to not feel the fear of getting on a rocket and launching into space and going to Mars. So I think fear is a very normal thing that all astronauts, in fact, are supposed to have. And I would be afraid to fly with someone who does not have fear.
Some psychologists worry that cabin fever could set in, and the crew might literally go crazy.
The human Mars mission is a more rigorous and difficult condition than most of us experience in daily life. But it is hardly a more difficult situation than many people have endured throughout human history. We could compare the Mars crew to the crew of 19th century or prior sailing vessels, many of whom were away from home for 3 years or more than 3 years, under conditions in which they're eating extremely bad food, without any medical knowledge to support their health, commanded by brutal officers. In every respect, the crew of a human Mars mission with the full support of mission support and the whole world cheering for them and great rewards awaiting for them in life upon their return, is in a vastly superior condition.
The Mars Direct crew will spend most of their time inside the 2-story hab, carefully designed to promote psychological well-being despite the confinement.
The space where I think everybody would spend the most time, just like a lot of homes on Earth, would be the galley wardroom area. There would be chairs, a table, some kind of large screen for entertainment. You would have individual staterooms about 4 or 5 feet wide. The ability for them to communicate with loved ones, with colleagues on Earth, I think will be almost unlimited.
A Mars crew will need to be carefully chosen and thoroughly tested to ensure their ability to handle the extreme isolation.
Wow, what a place. What a view, isn't it, John? It's absolutely unreal.
John Young, who went to the moon, used to say that he could cover the Earth by just lifting his thumb up to it. And he says that when you go to Mars, you are going to redefine the concept of loneliness. And so it is very important that the crew be well balanced and well chosen so that they can support each other.
Whoever gets picked to go, they will have to learn to live together for 2.5 years.
If you put out a call for volunteers for the first crew to Mars, they'd be lined up coast to coast. Most people recognize what's left after you go is the good you left behind. And to take part in a venture of this character, of such a historic character, of extending the reach of the human species, this is something of immortal significance. One of the most bogus threats associated with the Mars mission is the so-called back contamination issue, which is this notion that you go to Mars and discover these virulent disease organisms that you bring back to Earth and destroy all life on Earth.
If we discover life on Mars, one fear is that our Earth biology will have no defense against possible Martian pathogens. Some argue that missions to Mars cannot be risked until we can prove Mars is free from harmful contaminants.
This is completely nonsensical. There's natural transfer of material from Mars to Earth all the time. We get around 500 kilograms of unsterilized Martian rocks landing on Earth every year, and they have been doing so for the past 3-4 billion years. And so if there were Martian organisms that could contaminate the Earth, they've already done so.
Although the prospect of Martian diseases seems remote, lawmakers have required that NASA create elaborate protocol to ensure that any extraterrestrial material stays contained. And like the Apollo astronauts, who spent 17 days in quarantine after their return from a sterile moon, a Mars crew will have to be thoroughly tested for any harmful Martian pathogens.
The probability is infinitesimally tiny. But nevertheless, this is our home planet and it's extremely important and we have to protect it.
The idea of a pathogen on Mars is clearly ridiculous because there is no megafauna or megaflora on Mars for pathogens to infect. So it is impossible to propose a credible life cycle for a Martian pathogen. The diseases that afflict us have been co-evolving with us and our ancestors and near relatives for the past 3 billion years, and they are specifically designed to live inside the habitat of the human body and to overcome its defenses, and they've been engaged in an arms race with the human defenses for those 3 billion years. This is why humans do not get diseases from distantly related species. For example, I don't know of any person who has ever contracted Dutch elm disease, and trees don't get colds.
When the first Mars lander touches down, the crew will be staring out at a new world, a place that in 4 billion years, no eyes have ever seen. The crew won't be alone. millions of television viewers back home will be watching as the first man or woman places their footprint into the rust-colored soil. The crew will savor these moments, for here, someday, a new branch of civilization might begin, and future Martians will remember and celebrate this day. There is much for the crew to do and explore. One of their main mission objectives will be to search for signs of microscopic life. To do this, they will follow the ancient water flows. For on Earth, where there is water, there is life. To help the crew in their search, they will have a pressurized rover that allows them to explore in a comfortable shirt-sleeve environment. This means the crew can examine a vast area around the landing site during their 18-month stay. And there is much to explore. Mars has 58 different kinds of topography and a surface area equivalent to all the continents of Earth combined. If these explorers can uncover the fossilized remnants of indigenous Martian life, they will redefine mankind's understanding of its place in the universe. For if life arose separately on a planet so close to our own, it strongly suggests that the universe is a biologically rich place and full of life. For some, the ultimate question of Mars, though, is will there be human settlements on the planet? Will Mars become a new branch of human civilization? As each subsequent Mars mission explores a wider and wider area of the planet over several years, an ideal site for a base will be found, probably one with a thermal vent that can supply water and power. At that point, several HABs will be landed in this one spot, with crews that plan to stay for 4, 8, or even 12 years. The HABs will be interconnected, and a permanent human presence on Mars will be established. This scientific community will have to learn to become self-sufficient, to be able to survive on Mars without supplies constantly being sent from Earth. But unlike any other planet in the solar system besides Earth, Mars has all of the fundamentals needed to make this possible. Its 24-hour and 37-minute day is critical for growing plants. It has all of the elements necessary for creating building materials like plastics, metals, and glass. And it has oceans of water frozen into the soil.
If we can develop this craft of living on Mars, then Mars becomes inhabitable. Not immediately physically, but intellectually. I mean, look, what determines whether an environment is habitable or not? Is Colorado habitable? We're not naturally adapted to live in Colorado. We're tropical animals. No one could survive a single winter night here without technology, such as clothing, efficient use of fire. We invented our way into becoming people that could colonize such hostile environments.
Eventually, with a lot of ingenuity and invention, the scientists will learn to live off the land. They will grow crops in the iron-rich but potassium-poor soil. And they will produce oxygen and energy from the water and atmosphere. Sooner or later, children will be born, the first true Martians. They will grow up to see Mars as their home. With time, more and more people will arrive. These won't only be scientists, but settlers, people who plan to stay. They may come for all kinds of reasons, but to them, Mars will be a chance to start over, to build a new life for themselves.
The well of human social thought is not exhausted by the present age, and I don't think will ever be exhausted. There will always be people with new ideas on how humans should live together.
With Mars so far away, the hold of Earth governments on their colonies will be tenuous. The Martians will need to govern themselves.
Mars is not going to be a utopia. Mars is going to be a lab. It's an open frontier. It's a place where things are going to be tried out. I think we'll see a lot of noble experiments on Mars. Perhaps some of these Martian colonies with their novel ideas based on the best thought the 21st century has to offer, maybe they'll find ways in which humans create societies that are more humane and offer more opportunity for human potential.
The ultimate dream of the Martians will be to terraform their planet, to make Mars as hospitable as Earth. This may not be as big a fantasy as it seems.
Here we are on Earth, a world that's very sophisticated and developed and complete. And anything we do is just a subtraction. It's because we live in such a biologically rich planet. When we go to Mars, we have an opportunity that we don't have on Earth. Here's a planet that's died. Here's a world that's not full of biology, probably doesn't have any at all. Well, there, we can actually do something to help.
Once there are large human settlements on Mars that will have significant industrial capability, we could actually start addressing ourselves to the question of transforming the Martian environment itself, terraforming Mars, as it's called, because Mars was once a warm and wet planet, and it could be made so again through human engineering efforts.
With daytime temperatures in the Martian tropical zone averaging around 0 degrees centigrade, and with an atmosphere only 1% as thick as Earth's, exposure to these elements by a human without a spacesuit would be instantly fatal. The first step to terraforming Mars and bringing it back to life will be for the Martian colonists to warm up their planet.
Well, we know how to warm up planets. We're doing it on Earth by putting gases in the atmosphere. On Earth, it's not a good idea to warm up the planet. The temperature was just fine, thank you. We don't need it any warmer here. But in principle, if you could trap the sunlight reaching Mars today, every single photon that's hitting Mars, Mars would warm up in about 10 years. Well, obviously you can't trap every single photon that's hitting Mars, but you can trap about 10% of them with the greenhouse effect. So that would imply that Mars could warm up in about 100 years. Well, 100 years is a long time, but it's not astronomically long.
One idea is to build small, automated factories that produce super greenhouse gases with no ozone-depleting side effects. Although these gases would be unwelcome on Earth, for the Martians they would be an efficient way to trap heat.
Then within a few decades, we would raise Mars by more than 10 degrees centigrade. And if you did that, that would cause massive amounts of carbon dioxide that is currently absorbed into the Martian soil to start to outgas.
Carbon dioxide is also a natural greenhouse gas. As it builds up in the atmosphere, more and more heat will be trapped, which will in turn cause more CO2 to outgas. The process will become automatic, and as the atmosphere thickens, Mars will eventually reach a state of equilibrium and stay warm naturally. The rise in air pressure would mean that the human colonists could discard their pressure suits and walk around the surface of Mars carrying only a supply of oxygen. And as the temperatures rise on Mars, water frozen into the soil will begin to melt out. And for the second time in its history, Mars would have liquid water on its surface. Dry Martian rivers will start to flow. Seas will rise, and there will be rain clouds in the skies. The return of Mars to its warm and wet stage will make it a fertile environment for life. Any indigenous Martian organisms lying dormant will begin to grow, and Mars will be full of Martians. If no native life emerges, or that life is all dead, then humans could begin addressing the idea of bringing life from Earth. At first, it would be simple organisms, perhaps genetically engineered, that would thrive in the Martian environment. Then more complex plants could be introduced. The plants would be right at home in the carbon dioxide atmosphere, and with no competition and a whole planet to cover, they could transform Mars into a green world. Warming Mars so that it sustains life is rapid, but then the slow process of making the atmosphere breathable for humans and animals starts, and that's done by plants. Although the process will happen naturally, if the colonists can't find a quicker way, it will take tens of thousands of years.
This is a philosophical debate. Many people think the universe has a big sign on it that says, "Do not touch." Leave it alone. It was made this way. It is not in our purview as human beings to change anything. I can respect that view, although I disagree with it. I think the universe has a big sign on it that says, "Go forth and spread life." Because when I look around the universe, I think life is the most amazing thing we see. It is just incredible. And we human beings are uniquely positioned to help spread life from this little tiny planet, which it seems to have been started on, beyond. And that's our gift. Earth's gift to the universe, I think, is the gift of life.
This scheme for terraforming Mars is based on 20th century notions of engineering. I don't think it is how Mars will actually be terraformed. What you have here is a 20th century mind trying to address a 22nd century problem. And so I think Mars will be terraformed by the 23rd century, not by the 33rd, by the 23rd. Things that would seem utterly fantastical to us is how it will actually be done, but it'll be done. We're at a crossroads today. We either muster the courage to go or we risk the possibility of stagnation and decay.
The exploration of the solar system and expanding of life through the rest of our solar system and someday beyond is the kind of thing that will keep our civilization going.
We're explorers by nature. Eventually we will go to the stars. And the question is, when will we start?
I think a manned-Mars mission could happen within 15 years.
Some days I'm very optimistic. I think we can do it in 10, maybe 15 years. Other days I see all the political things that go into the space program. I look back on the 30 years we've been bogged down, and I get more negative about it, and I say it's going to be another 3 decades or 4 decades.
I would be surprised if we got to Mars prior to 2025 or 2030.
In May of 2018.
Understanding the various political obstacles that exist and what we need to fight through to get the program started, I believe that we will be on Mars by 2020. You have to believe in hope. You have to believe in the future. There are more and more people coming around to the point of view that a positive future for humanity requires human expansion into space. We will eventually break through the forces of inertia that have been holding this thing back.
viewers of a NASA video feed from the Space Shuttle Endeavour reported seeing a disc-shaped object hovering above the shuttle's mechanical arm. Space-based UFO sightings like this have purportedly happened throughout the history of manned spaceflight. Unspecified cosmic phenomenon? Or could it suggest the possibility that huge extraterrestrial starships are cruising the Milky Way galaxy?
Space travel between the stars, it's a staple of science fiction, right? You see it every night on television, you see it in the movies all the time. But could we really do it, or could any species really do it? Well, the distances between the stars are enormous, really enormous. Interstellar travel doesn't violate physics. It isn't that you can rule it out and say, there's absolutely no way they can come here. It's just that it's very, very hard.
Just traveling from the Earth to Alpha Centauri, our closest neighboring star at nearly 4.5 light years, is beyond the reach of our most powerful rockets.
If an advanced civilization were to visit us from a distant star system, we can pretty much rule out that they would use chemical rockets to get here. Despite the impressive pillar of fire and smoke that we see during Apollo, Saturn V, or shuttle launches, chemical rockets don't get you very far in the solar system.
To give you some context for that distance, our furthest known space probe is Voyager 1, launched in 1977. It's been flying for 34 years at 38,000 miles per hour, and it's only now starting to leave our solar system.
If its destination were Alpha Centauri, it would take over 56,000 years to reach even the closest star system. To engage in interstellar missions on timeframes of a human lifetime, around about 50 years, we can see that we need to increase the speed that we can travel by at least a factor of 1,000.
Scientists have determined that the speed of light is a mind-blowing 186,000 miles per second. A spacecraft traveling the star system would have to reach a significant percentage of that speed, even to reach the nearest star. The biggest obstacle is weight. A chemical rocket exacts a huge weight penalty because its entire fuel supply must be carried on board.
We can calculate that even to reach 6% of the speed of light using chemical rocket fuel, you would need more rocket fuel than exists mass in the universe. So we really know that it's actually impossible to reach another star system using chemical rocket fuel.
If extraterrestrial visitations are even possible, their spacecraft must solve this problem. In 2011, NASA's NanoSail D became the first solar sail to orbit the Earth. The ultra-thin 100-square-foot sail uses sunlight, or photon pressure, as a source of propulsion.
One of the immutable limitations of rocket propulsion is the fact that any rocket has to carry its fuel with it. A solar sail can take advantage of the naturally occurring resources, namely photons emanating from the sun, which can be used to propel that solar sail. Similarly, a hang glider can fly without any fuel or an engine just by taking advantage of the natural resources we're surrounded by, namely the atmosphere and the laws of aerodynamics.
To achieve sufficient speeds to tow a spacecraft supporting life forms, the sail would have to be huge, up to hundreds of miles in diameter. And because the photon pressure from a star would decrease the further the sail traveled, some have envisioned a concentrated laser beam directing energy at the sail.
Eventually, and sadly, this hang glider and all hang gliders at some point have to land. But a solar sail riding a beam of laser energy could conceivably travel to the stars.
The max speed of a solar sail? About 10% the speed of light. Travel from Earth to Alpha Centauri using laser-generated photons? About 45 years. Currently, NASA and other space agencies have plans for launching more solar sails. But there are other, more powerful sources of propulsion in the universe.
In the 1960s, a method of propulsion was proposed where a spacecraft would literally drop a series of explosive charges out the back, and the force of the explosions would push the spacecraft forward. The prototype was called the Orion drive, and there were actually a series of experiments done with conventional charges to show that it would work. The Orion drive, however, was proposed to use nuclear charges. In order to simulate an Orion-style propulsion system, Paul and Jim here are rigging up a demonstration where they're going to put a small chemical charge inside this barrel, and we're going to lift this off the ground 50, 60 feet in the air. We're going to actually calculate the energy released in this explosion and compare it to a nuclear charge you might find on an actual Orion spacecraft system. Our Orion spacecraft simulator is rigged and ready to go. We're going to light off the charges inside, blow the can up into the air, and compare that with the energy released from a typical nuclear explosion that would be used on an Orion-style drive.
The Orion spacecraft, studied at Los Alamos in the late 1950s, proposed nuclear fission as its propulsion source. Fission energy is produced when the nucleus of an atom splits into smaller parts, producing free neutrons and protons that release tremendous gamma-ray energy.
The explosive charge in this 35-pound barrel lofted at about 60 feet in the air. A small nuclear charge in the Hiroshima range would liberate about 27 million times more energy. Clearly, that's a practical propulsion drive for interplanetary or even interstellar travel. Because of the huge explosions that an Orion drive would require, on the back of the spacecraft, you would have a huge, thick metal plate that would absorb the thrust of the explosion and a series of shock absorbers to keep the crew from getting jolted each time the charges went off.
The max speed of a nuclear-powered fission spacecraft? About 5% the speed of light. Travel time from Earth to Alpha Centauri? About 90 years. Despite its powerful fuel source, the fission craft is actually slower than a solar sail. Boosting speed would mean turning to another, more intense nuclear reaction.
Fission technology is well known and understood, and we've been using it to generate power here on Earth for decades. But there's another kind of nuclear technology, and that's nuclear fusion.
Fusion is the power source of the sun. In the core of our sun, the temperatures are so high, atoms are moving so fast that they slam into each other, creating new elements and liberating energy.
The opposite of fission, fusion energy is produced when two atomic nuclei fuse together to form a single heavier nucleus. The result is a huge liberation of energy. A fusion-powered spacecraft was proposed in a 1970s study called Project Daedalus. Its mission called for a trip to Barnard's star, some 5.9 light-years distant. Instead of nuclear bombs, the fusion-powered craft creates the propulsion on board in a reaction chamber.
The fuel pellets for the Daedalus-class starship consisted of pellets composed of a deuterium helium-3 mix. These would have been ignited by what we call relativistic electron beams. These are extremely high-energy electrons that would have hit the deuterium helium-3 pellets, caused them to fuse, and a huge amount of energy would be released. The Daedalus design called for 250 of these pellets to be released every second for over 2 years. The spacecraft would have weighed 55,000 tons, most of which would have been fuel.
The weight penalty for such a spacecraft would be high, but an advanced civilization could eliminate the problem by mining the hydrogen fuel during its interstellar journey. Deuterium, or heavy hydrogen, exists in abundance on Earth, notably in seawater. But helium-3 is a much rarer isotope. In our solar system, it can be found on the Moon, and in vast quantities on Jupiter and Saturn. Scientists have proposed using huge hydrogen scoops to mine the helium-3 needed to cross the void of space.
So it's conceivable that if you had a craft that was powered by nuclear fusion, you could go to another star system and then use the hydrogen available from that star to refuel.
The self-contained, fusion-powered spacecraft could avoid a huge weight penalty and reach speeds that could allow near-star exploration in a reasonable time frame. The max speed of a nuclear-powered fusion spacecraft? Up to 15% the speed of light. Travel time from Earth to Alpha Centauri? About 35 years. The immense costs, the logistics, and even the politics of nuclear-powered spaceflight long ago caused humanity to scrap any and all plans. But a sufficiently advanced society could trade nuclear propulsion for what seems like an impossible paradox, traveling at light speed without moving at all. Can UFOs actually achieve the immense speeds required for interstellar travel? One potential answer may be buried 30 feet beneath the ground in America's heartland. The Fermilab Tevatron Collider, outside Chicago, Illinois. Racing just below the speed of light, particles of protons and antiprotons are launched in opposing directions. They meet in a high-energy collision. The impact produces gamma rays, the highest energy source known in the universe, and potentially the key to interstellar travel.
The best way of making antimatter here on Earth is to employ probably the most famous equation that Einstein taught us, which is E = mc squared, which tells us that for a certain amount of matter we can get energy. It's a great idea because it's incredibly efficient. You essentially take all of the mass in those particles and convert it into energy.
But how can antimatter exist in the universe if it must be artificially manufactured? That's the question that Stephen H. from Philadelphia texted the universe.
Stephen, antimatter definitely exists, and when it meets up with normal matter, it explodes in a burst of electromagnetic radiation. Now, we can make small bits of antimatter in laboratories, but we can also collect antimatter from space. Some cosmic rays, which are charged, very energetic particles coming from space, actually consist of antimatter.
Currently, the Super Collider is the only practical way to produce antimatter. And right now, it's created in very small quantities.
If we could figure out a way to both create and store enough antimatter, we would have a storable fuel which, when mixed with ordinary matter, would liberate a huge amount of energy at a rate way beyond what either fission or fusion can do.
Because we know antimatter exists, and we know antimatter can be created and stored, it is conceivable that an advanced civilization could create and harness the power of antimatter in sufficient quantities to create an antimatter rocket.
An antimatter ship could achieve unbelievable velocities, cruising just below light speed, nearly matching the speed of a starbeam streaking across the galaxy. Travel time from Earth to Alpha Centauri, 4.5 light years distant, about 5 years. In human terms, the cost of creating enough antimatter particles to power such a starship would be astronomical. It might be affordable in alien currency, but an antimatter spacecraft like this comes at a high price. The gamma rays from antimatter propulsion are so dangerous, they could destroy the cell structure of any living beings aboard ship. This starship would have to include an advanced shielding mechanism to keep the crew alive. And at such high rates of speed, there are equally destructive threats in the universe.
Space is pretty empty, but if you were moving close to the speed of light, you'd need an extremely effective shielding system that would allow you to be protected from interstellar dust particles that would all but annihilate a spacecraft traveling that fast.
But if space debris is so dangerous, why not avoid it completely? The solution might be one familiar to Star Trek fans, namely a starship that could achieve light speed without even moving.
In effect, one would create what is called a warp bubble, the name taken straight out of science fiction, and that would involve compressing a region of space-time in front of a spacecraft and expanding a region of space-time behind a spacecraft, while the spacecraft itself sat stationary inside this flat bubble. And one would effectively be riding a wave of space-time.
A warp drive may seem like pure sci-fi fantasy, but in 1994, a well-respected young physicist named Miguel Alcubierre published a serious proposal outlining how to travel in a controllable space warp. There are huge obstacles to Alcubierre's warp drive solution. The biggest is called dark energy, a cosmic phenomenon recognized in 2011 when 3 scientists were awarded the Nobel Prize for proving its existence.
The simplest explanation that's been proposed for the phenomenon of dark energy is that there's an intrinsic property of space itself that makes it want to expand. You can actually see it by looking at receding parts of the universe and seeing that there's this extra acceleration component, but it isn't a stored energy source like solar energy or other kinds of energy.
And so it's not inconceivable, it's not beyond the realms of possibility that some advanced civilization existing somewhere in the universe has learned how to harness dark energy to create an exotic form of propulsion.
But there's another obstacle to a workable warp drive. The only known way to pull a spacecraft forward within a warp requires harnessing the intense energy of a black hole.
The sort of simple notion is somehow to make a very concentrated bit of matter, extremely concentrated on the level which would cause a black hole. If you could generate a black hole on a small scale, so to speak, you could dangle it in front of the ship and use its space distortion to sort of drag the ship along.
And exactly how fast could a warp drive tow an extraterrestrial spacecraft?
The clear implication of Alcubierre's work was that it should be possible, if you can make his design of a warp drive, to achieve speeds almost any multiple of the speed of light.
Travel time from Earth to Alpha Centauri aboard a lightspeed craft powered by a space warp? About 4.5 years, or less, as long as everyone on board doesn't incinerate.
One problem with the Alcubierre drive is within that warp bubble, temperatures would rise to far hotter than the core of our sun. That's hot.
Just one more small problem to solve for the chance to reach planet Earth. But what if such an alien spacecraft were to arrive in Earth's atmosphere, riding in a warp bubble towed by a black hole? It might not be the first mass witness UFO sighting, but it would certainly be the last. March 13th, 1997. Thousands of people witness an optical phenomenon drifting across the Arizona skies. Reports of a series of bright lights in geometric patterns are widespread, including multiple sightings over Phoenix of a craft up to 1 mile wide with lights winking on and off in sequence.
Reconstructing the events of that evening, the lights of the Phoenix Lights were almost certainly flares dropped by an Air Force A-10 aircraft in conjunction with the human tendency to envision a solid shape connecting them. That's the best explanation for the Phoenix Lights.
For many, the Phoenix Lights incident was direct proof that a huge extraterrestrial craft had arrived. Some even called it a mothership. The purpose of an extraterrestrial mothership is fundamental to the theories of alien visitation. It's the only way to bridge the vast distances of interstellar space.
The term mothership, I think, came into being around the same time that flying saucers as a term came into being. And I think the universal notion was you couldn't make an interstellar trip in a person-sized craft. You had to have something really large.
An apt earthly analogy of a mothership is that of an aircraft carrier. An aircraft carrier travels the vast distances across the oceans, but its purpose is to transport smaller aircraft which can then go on and engage in whatever their missions may be.
If the journey to Earth is long, on the order of centuries or even millennia, the mothership would be much more than just an aircraft carrier.
There's the generational or arc ship, which is a very large spacecraft that is essentially an enclosed ecosystem in which generations of inhabitants expect to be born, grow old, and die over the long period it takes the spacecraft to reach its ultimate destination.
Perhaps with technology such as suspended animation, biological alien passengers could be put to sleep and revived after the vast journey. Surviving such a journey would also mean surviving the destructive energy powering the spacecraft itself. One logical design solution, a cigar-shaped mothership, is precisely what many UFO witnesses claim to have seen.
For any advanced propulsion system, you would want to situate the crew as far away as possible from the engine source. So one possible design would be a very long, thin design with the engine located at one end of the spacecraft and then some kind of truss connecting the crew section as far away as possible so as to avoid damage from high-energy neutrons, X-rays, or gamma rays from the advanced propulsion system.
If such arc ships have in fact visited planet Earth, the evidence would be overwhelming and undeniable.
Something all these exotic and advanced propulsion technologies have in common is that they all radiate prodigious amounts of energy, and so we'd be able to see them like beacons on a lighthouse from sometimes light years away.
A concentrated emission of X-rays, gamma rays, or subatomic particles would be suspicious because we don't see that in our environment locally under any normal circumstances.
Beyond the obvious visual evidence, the physical effect of a mothership approaching so close to the Earth's surface could be a terrifying form of apocalypse.
If for whatever reason this extraterrestrial technology or civilization chose not to turn off their engines, it could be catastrophic for life on Earth, as we would be bathed in high-energy neutrons, X-rays, and gamma rays.
If it's something which is a version of a warp drive, then you're talking about space distortion. And you wouldn't want to be too close to any major mass, including a planet.
Such catastrophic visitations assume that aliens are willing to risk their own lives in interstellar space. But there might be a better way. They could stay at home and explore the cosmos using a race of thinking machines. For many ardent believers in the UFO phenomenon, the Roswell, New Mexico event in the summer of 1947 is the defining alien encounter in human history. In popular culture, the most lasting detail from the purported crash came from the descriptions of extraterrestrial bodies found at the scene. In the ensuing decades, this vision of alien beings, known as the Greys, became the accepted standard in science fiction and recurring alien encounter reports. The oversized heads may explain an expected feature in alien biology: greater intelligence. The larger skulls would contain larger, more advanced brains compared to ours. Mastering the profound challenges of interstellar travel would certainly require great intelligence. But might it require something that is beyond organic biology?
One area of science fiction where we might be making kind of a big mistake is to assume that the aliens are biological, that they're living things.
I think that the possibilities for the kinds of organisms which might travel between the stars are really wide open. And one possibility that has appeared on occasion in science fiction is machine intelligence.
According to a recent earthly equation, known as Moore's Law, the number of transistors on a single computer chip doubles every 18 months, meaning computer processing speed doubles. This trend has continued for more than half a century and is expected to continue through 2020 or later. The exponential explosion of processing speed is opening the door on a staple of science fiction called artificial intelligence.
So if you invent a thinking machine, 100 years later, that machine is not only smarter than you are, it's smarter than all humans that have ever lived. And that's the difference between artificial intelligence and real intelligence. Artificial intelligence can evolve enormously faster. But I think the form of AI that we find most both menacing and promising is the kind of AI that could, in fact, do what our brains can do, can think the way we can think.
At Stanford University's Artificial Intelligence Laboratory, the future of truly intelligent machines is rapidly approaching.
There are a few things that make AI difficult. One is we don't really know yet how to make computers learn as effectively as humans can. It seems that our computers today just aren't as fast as we would like them to yet to simulate the learning processes that take place in the human brain.
To demonstrate early-stage artificial intelligence, Stanford students designed a fighting robot, one that attempts to learn as it fights.
Okay, so what it's doing now, it's trying to defend itself. So it's reacting to your motion. So depending on how you move your sword, the robot will adapt to your motion and to your behavior.
How important a step on the road to true artificial intelligence are robots like this, Thorsten?
So here we are using artificial intelligence methods, like learning methods, to adapt to the environment of the robot. But we are still not at a stage where the robot is really thinking.
Today's computers are still far less intelligent than almost any human, but in the future, I think computers could eventually reach and maybe even surpass human intelligence. And if that's the case, imagine that each of us had a computer in our wallet, had a cell phone in our wallet that was as smart as Einstein or even smarter. How would civilization change, and what are the amazing things we could do then?
Advanced as it is on Earth, the fencing robot is but a crude analogy for the type of machine intelligence that could pilot an interstellar spacecraft. The immense obstacles of space travel, including the sheer timescale and cosmic hazards, build a strong case that a race of intelligent machines will make first contact.
But honestly, if interstellar travel really takes place, it seems sort of reasonable to not send the biological beings. I mean, they're fragile. They have finite lifetimes.
Just as NASA sends robotic probes to explore the solar system in advance of human explorers, our first contact with an alien civilization may be with its robotic probes.
Biologic being or AI super being? Our vision of an extraterrestrial will remain mere speculation until first contact is made. But how long will we wait? And despite a lack of hard evidence, just how likely is the existence of another intelligent civilization? some believe it is highly likely that the universe teems with life.
The galaxy has been around for a long time. The solar system has been around for quite a long time, but the galaxy much longer. And the stars in it, many of them are much older than the sun and our solar system. So the chances are civilizations are out there. They've been around for longer than we have. If they exist, say, for 100,000 years, then the chances are pretty good, I think, they will have learned to either communicate across interstellar space or possibly travel.
Until first contact occurs, humanity will continue to scan the skies for UFOs. None have been proven to be extraterrestrial craft so far, but that does not rule out the possibility that humanity may one day discover evidence of an intelligent civilization, either in the far-flung heavens or much closer to home. In space, no one can hear you scream. As the promo line for Ridley Scott's science fiction film Alien, it was designed to send chills down your spine. It's based on the unsettling idea that space is a vacuum, and sounds, whether screams, shouts, or songs, can't travel in a vacuum. But is that really true?
Well, it's kind of narrow to think that in space you can't hear anyone scream, because in fact, here on Earth, there are lots of sounds we can't hear. They're either too high a pitch or too low a pitch. Moreover, space isn't completely empty. And then finally, you know, what's the definition of space? If I'm an astronaut on the surface of Mars and I have a spacesuit on, am I in space or am I not? Well, I would think I am.
Okay, let's try right over here.
Back on Earth, Bruce Betts of the Planetary Society in Pasadena, California, has given a lot of thought to Mars and the subject of sound. He's programmed his computer with what he calls the Marsinator to demonstrate what his voice would sound like in the cold carbon dioxide atmosphere of Mars, without those spacesuits.
The atmosphere of Mars would actually change your voice so it sounded deeper. So let's go ahead and simulate that using the Marsinator. And I will record my voice, and then we will shift it to what it would sound like on Mars. This is what I'd sound like on Mars, although I'd be wishing I had some oxygen to breathe. Then I go ahead and process it, put it through the Marsinator, and then we play it back and see what it sounds like.
This is how I would sound on Mars, although I'd be wishing I had some oxygen to breathe.
Of course, if humans ever do make it to Mars, we will not hear their voices through the atmosphere. Instead, we'll get them via radio waves, the way many of our most important sounds already reach us.
Yes.
We're familiar with thinking of sound as something that comes through the air to us, just like we hear each other when we're talking. But in fact, a lot of the sounds that we hear are transmitted through electromagnetic signals. For example, your television actually transmits a television signal into sound that you can hear.
Who's our first contestant tonight?
Sound in the cosmos will never reach us directly across empty space. So radio, light, or other electromagnetic waves are the inevitable carriers, bringing us a universe we can hear in all its variety.
Space is actually kind of a noisy place. It has many, many sources of noise that we are able to detect with special radio telescopes, for example.
These alien sounds make up an incredible collection, the ultimate playlist. We've polled our expert panel of scientists, astronomers, and physicists to rank the top 10. The greatest sounds from the expanse of space, ending with a number 1 that will surprise us all. And now the countdown starts. Coming in at number 10, ringing out from a distance of 13 billion light years, the birth cry of the universe in a hit called The Audio Afterglow of the Big Bang.
It's remarkable that the young universe actually made a sound, and the reason we know that is that we can actually witness the glowing gases that were present at that time.
The glow from these gases is known as the cosmic microwave background radiation, or CMBR. It is a faint trace of microwaves that stretches across every point in the sky. Discovered by scientists in the mid-1960s, the radiation is the afterglow of the Big Bang. The famous blotchy satellite map of the CMBR represents the cosmos in its infancy, when it was only 380,000 years old.
When we look at the CMBR map, we're essentially looking at a voice print of the early universe, because those tiny variations in color correspond to variations in temperature, and those correspond to variations in density and pressure. Well, pressure waves are just sound waves, so we're seeing little variations in pressure, little sound waves in the early universe.
To understand the audio afterglow of the Big Bang, we need to know how the early universe varied its pressures to generate sound waves. To find out, astronomer Mark Whittle and organ builder Manuel Rosales visit the magnificent pipe organ at Claremont United Church of Christ in California. In a way, the 4,000 pipes in this organ are comparable to the voice of the early universe.
Manuel, the amazing thing about the early universe is that all its pipes were sounding together. And it'd be lovely if we could just try that with this organ. So do you think we could do that now, play all the notes at once?
Yes. Let's pull out all the stops and try it.
Ah, that's where that phrase comes from.
Yes.
Okay, let's go. Very powerful, but really hissy, white noise kind of sound. But an even more remarkable thing about the primordial sound is that, in fact, a few particular tones were present and were stronger at any given time.
This is the opening note of hit number 10, the audio afterglow of the Big Bang. A computer sound analyzer reveals its strong tones as distinct columns on a color-coded graph. As hissy as the early cosmic sound is, it differs from pure white noise, which has no organized features at all on the analyzer. The sound of the audio afterglow, on the other hand, comes through with a vaguely musical quality. The pipes of this or any organ are made of wood and metal, but the pipes of the early universe were pits of dark matter, the mysterious substance whose existence is known only from its gravity.
What drives the sound waves is gravity. So, for example, if there's a region of slightly higher density of dark matter, there's a gravitational force pulling in. Gas that's surrounding this region feels that pull and it falls in, but it's gas, so it also, as it falls in, it compresses. That compression acts like a spring, and so it pushes the gas back out, but then it overshoots until it falls back in again. And this is how the motion of the gas falls in, bounces out, falls in, bounces out, so we have an oscillating pressure wave, a sound wave.
The cosmic background radiation, as important as it is just a still picture. Its imprint of sound has the effect of no more than one noisy, barely musical note. And even hearing that is a struggle. The pipe organ helps show us why.
The sounds of the universe are way too low for us to hear. In fact, what's the lowest note that this organ plays?
It is a pipe 32 feet long, and it can only be played with one's foot.
Yeah, that's pretty deep. Well, 32 feet were nothing compared to the cosmic organ pipes. They were between 20,000 and 400,000 light years across.
Sorry, we don't have any pipes quite that long.
No.
The deep sound of the early universe is so low, we can hear it only after a massive shift upward. The background radiation of the universe dates from 380,000 years after its creation. But what happened before that? Is it possible to uncover the whole song of the universe from the very instant of the Big Bang? The cosmos is filled with a symphony of alien sounds, and we're counting down the top 10 of the universe's greatest hits. Number 10 on the playlist sings out with the earliest tones of the universe, from the audio afterglow of the Big Bang. But our download of the universe's birth song has some problems. With the cosmic organ playing all its pipes at once, what reaches our ears sounds like only one complex, noisy note. It's only one note because it comes from the pressure waves we read from the map of the cosmic background radiation, which is just a still picture of the sound in the early universe, taken 380,000 years after its birth. How then do we run the clock backwards and hear the rest of the song?
Modern cosmology is sufficiently advanced that it's possible to create a computer replication, a simulation of the young universe. It's possible to recreate within a computer what's going on and how the sound developed right from the very, very beginning through those first 400,000 years.
They are the same kind of supercomputer simulations that have given us pictures showing how the early universe evolved. The dark matter pipes of the early universe acted like those in the church organ. As bigger pipes were played, deeper notes were sounded. As the universe expanded, there was more space and more time. More space meant bigger pipes, so the notes in the song got lower and lower as the song played out. Put it all together, and the first 400,000 years of the universe can be condensed down to just 10 seconds. A haunting primal scream.
The gas that's falling in and out of these dark matter regions is ultimately going to become the first stars, the first galaxies, and ultimately it'll be corralled into the thousands of galaxies that we see around us today. So while it's been amusing, really, and playful to reproduce these sounds for us to listen to, in the big picture, they play an enormously important role in crafting the structure of the universe that's going to unfold, and the universe that we find ourselves in today.
From the big band sound of the Big Bang, our countdown takes a step down in size to the modest 15 million light-year span of a galaxy cluster. Coming in at number 9 on our list of the universe's top 10 hits is The Deep Tone of Perseus. This is low sound to the extreme, emanating from the Perseus cluster, a grouping of roughly 1,000 galaxies, 250 million light-years from Earth.
The central galaxy in this cluster of galaxies has a huge supermassive black hole at its center.
The cluster's central galaxy is called Perseus A, and its supermassive black hole gives it what's called an active galactic nucleus, which shoots out energy in the form of gigantic jets, tearing into the surrounding space.
For reasons which we don't fully understand, it seems to be coming out, the energy is being produced episodically, about every 10 million years or so.
Those energy pulses are actually waves of pressure. And that's exactly what sound waves are. Pressure waves. The wave, as demonstrated by sports fans, has an up and down motion that's very familiar to us. But these UC Berkeley students will switch gears and show us how a sound wave is different.
Okay, everyone, lose the pom-poms. Since sound waves are pressure waves, we're going to build a pressure wave out of all these students. Okay, everybody, let's line up. You go over here, and then shoulder to shoulder, just like this. Stretch out over there a little bit. No gaps. You're going to be students colliding with each other like molecules colliding in a sound wave. That's looking a lot better. Do you feel like a bunch of molecules? Okay, this is looking good. We have a bass drum at each end of the line. You'll see why in a minute. We'll get things going with this drummer over here. He's going to hit the drum and watch what happens. In this case, the pressure is a good, healthy shove, and it moves from student to student all the way down the line. At the end, the last student applies his pressure to the second drum by banging on it. The second drum is like our eardrum. When pressure from a sound wave in the air hits our eardrums, we hear the sound. This is just how sound travels through the air, except instead of having students shoving each other, there are air molecules shoving each other. A sound needs a medium to travel through. It can't travel through a vacuum. So in fact, to get from point A to point B, you need air molecules hitting each other. That's how it works.
So how do those pressure waves from number 9's deep tones of Perseus travel through what's essentially the vacuum of intergalactic space? Astrophysicist Richard Pogge of Ohio State University gives us a sense of the emptiness in deep space at his school's football stadium.
Well, it's true that sound waves can't travel through the vacuum of space. Space is not a complete vacuum. I'm here in Ohio Stadium, home of the Buckeyes. It's very empty today. I'm the only one here, and can't think of a better place to illustrate the vacuum of space.
The empty stadium can be a stand-in for the vacuum of space if we compare it with what it looks like on game day. With more than 102,000 people in its seats, Ohio Stadium would be like the atmosphere on Earth, jam-packed with air molecules.
So how much do we have to clear out this stadium to equal the vacuum of space? Believe it or not, you have to clear out everybody, including me, and then even I'm too much.
No more than a single cell from Pogge's body could remain in Ohio Stadium to come close to the vacuum of deep space. With what seems like almost nothing in the expanse between galaxies of the Perseus cluster, the existence of sound waves seems all the more incredible.
How do you propagate a sound wave through empty space when it's mostly empty? Let's use the example of me running down the field. I have to run a long ways before I encounter somebody, but I still encounter somebody and I can pass energy along to them. The same is true of atoms in interstellar space. It has to travel a long ways, maybe 300 light years before it encounters another particle, but when it encounters it, it passes the energy and the wave moves along.
The colliding particles in the Perseus cluster also emit faint X-rays, whose traces, imaged by the Chandra Space Telescope, tell us the waves are there. But these waves are huge, and the notes they produce are lower than anything any human has ever experienced.
The pitch is about 57 octaves below our hearing, below the middle of a piano range, and that actually qualifies this for the Guinness Book of Records as the deepest pitch known to man.
The extreme deep note emanating from Perseus is so far below our hearing range that it can only be approximated. It's been said the galaxy cluster is playing an awesomely low B-flat, and scientists calculate it'll be playing constantly for 2.5 billion years. Number 9's Deep Tone of Perseus drones on as the countdown advances. A secret number 1 waits at the end of the line, but first, a strange high-pitched squeal hints at what comes in at number 8. Sounds from space and their link to signals from extraterrestrials. Starting with the Big Bang, we've been tracking the top 10 of the universe's greatest hits. The best of the alien sounds from space. Jumping to number 8 on the countdown.